Good morning, students. So, in the last class, we have discussed that is the fluid dynamics. So, in the Euler equations, Bernoulli equations, and fluid in the rotations, rectilinear motion, all we have discussed. But one thing that is the in fluid dynamics, one more that is the equations which I have to discuss, that is called Navier-Stokes equations. Momentum equations I have discussed, but momentum equations of the fluid flow generalized I have not discussed for a control volume. I have discussed momentum equations for a fluid striking the wall or moving plate, like that we have discussed. Here we have to discuss the Navier-Stokes equation or conservation of momentum for a fluid element. So I am going to the load the note. All of you got the note of the fluid dynamics? हेलो, फ्लूइड डायनेमिक्स की नोट मिल गया है ना? Tell me, you got it or not?
Yes, sir.
Okay. Is it visible?
Yes, it's visible.
Okay, thank you. Navier-Stokes equations. So actually generalized momentum equations in the fluid flow element, it is given by the Navier and Stokes. That's why it is called the Navier-Stokes equations. But generally this is the conservation of momentum at a fluid element. Conservation of the mass or continuity, we have discussed conservation of the momentum for a fluid element, whose that is the volume is dV. So change of momentum in such a fluid element we have to study. So momentum is the product of mass and velocity. This is the well known. So the fluid inside the volume has a momentum. Mass into volume. So mass into that is the velocity. Here see density, as I told you, mass into volume. So density is represented here, mass, and V, that is the rate of the mass. So this is our control volume. Here I am showing you. This is the control volume whose length is dx, dy, dj. So first that is the C here, just then I will come there. So the fluid inside the volume has the momentum rho into dx into dy into dz, volume into V. Here V, that is the bold, that is the in vector, not that is the velocity component along y depth. This is the velocity vector and its rate of change can be written. So del y del t into that is the mv, that is written in the term of rho dx d, and dx dy dz is a not function of t because it is itself an independent variable. So del y del t into rho into v. So in generalized, we can say that the rate of change of momentum in a volume element or fluid element equal to the summation of the momentum fluxes entering the volume element minus the momentum fluxes exiting the volume element plus shear and normal stresses acting on the volume element plus forces acting on the mass of the volume element. Again, I am going to read it. So the rate of change of momentum for any fluid element equal to the summation of the momentum influx. Influx means entering minus leaving. That is the influx plus shear plus that is the stresses acting on the our fluid element plus due to the mass or weight of the fluid element. All these are the equal summation. So this is the generalized, that is the our principle. So first we will consider the one component, that is the of our given generalized mass, that is the rho into dx dy dz into v. We will take first along the x-axis. So this will become rho y del t rho into u dx dy dz. So first we are considering the momentum along x-axis. So rate of change of momentum along the x-axis equal to the del y del t into rho into u into the volume dx into dy. So mass flux momentum entering or exits the volume through the surfaces of the volume element per unit time. So continuity question already we have discussed. So now we consider the quantity rho into u, momentum per unit volume. So the continuity question, we write down the momentum fluxes entering and exiting the volume. So the momentum flux. So initially we restrict ourselves x direction of the rate of change of momentum. So rate of change, so that will give you entering, and this is the entering, that is the flow along the x-axis and it crosses and passes through the surface area other than the x-axis, that is the here c dx, that is the other than dx is dy dz. Here that is the flow, that is the entering and exiting along the x-axis with all components are written. When any fluid, that is the any that is the our fluid entering the flux inside a control volume also affecting the other direction. So that is the here written, that is the entering. So the quantity, so entering the left surface dyz of the volume is quantity rho into u changes its value in the x direction. So mv, so rate in, that is the rate of the mass into the velocity. So here that is the mass is nothing, rho into u into dx d, that is the into per unit volume, so that is the into u. So flow takes place along the, yes, flow takes place in the control volume along x-axis. So mass into that is the velocity. So rho dot u into u and passes through the cross-sectional area dy dz. This is the entering, that is the left side. See the face here. Rho dot u. This is the entry. And leaving, so that is the changes due to the fluid element length dx. So rho dot u plus del y delta x into the parameters which is entering and leaving, rho dot u velocity along x-axis into dx plus higher order term which we have truncated or eliminated from the Taylor series. It is a rectangle. So this will become here that is the rho dot u dot plus del y del x rho dot u into dx surface area dy dz. So the momentum rho dot u acting in x direction also enters and exits the volume element through the remaining surfaces such as dx dz. So dx and dz, that is the front surfaces is showing. Then dx dy, so dx, that is the, and dy, that is here showing, that is the top. So this is the your dx dy, that is the top. So top and bottom, so with velocity component v and w respectively. So V is passing through the other than the y direction, means that is the dx dz, w passing through the dx dy. So similar expression can be written down for the y and z direction. So see, this is the due to the flow or entering along the x-axis momentum, and it is also affecting the y direction and z direction. So all components are written here along x-axis. Rho dot u means mass into the velocity. Mass, that is along x-axis, is rho into u. Mass along the y-axis is rho dot v, and momentum due to the velocity component x-axis u is product of the u. So rho dot v dot u. Similarly, z-axis rho dot w is mass dot velocity along x-axis u. So this is the about the x-axis here, and due to the fluid element length dx dy dz from the Taylor series, it is written here rho dot v dot u plus del y del x rho dot v dot u into dx. So see, velocity component along the x-axis. That's why we are differentiating with respect to that component length dx, affecting the dx of the all mass along x-axis, y-axis, and z-axis. So rho dot v, rho dot u, rho dot w, these are the mass along x-axis, y-axis, z-axis, and changes due along the dx. That will give you plus del y del x into dx, and velocity along x-axis. Second here, along, that is the written here y direction. So velocity component v is multiply in each mass rho u dot v, rho v dot v, rho w dot, that is the, here see, this is the v, not the u. In second figure, that is the upward, rho dot w dot u is written. This is the wrong. This is the rho dot w dot v, because we are discussing momentum along the y-axis. So velocity component of the y-axis is v. So everybody, the last product is the v. So rho dot v dot v, rho dot w dot v. Note that is the u. And in that is the due to the fluid element length del by dy. So that's why it is a differentiating and multiply by that length. Similarly, we can write for the third direction dz. Am I right? So rho dot u dot w, rho dot v dot w, rho dot w dot w. This is the normal, that is the momentum entering the surfaces of the first side. That is the left, bottom, and that is the along the y-axis. And due to the length of the fluid element, dz changes, which is also given in the figure. So now the momentum fluxes entering and exiting are not only due to the rate of change of momentum within the fluid element. Momentum fluxes entering and exiting are not only the cause of the rate of change of momentum within the volume element. The momentum inside the volume element is also changed by the forces acting on this volume element. And these forces include the normal stresses and shear stresses. And these stresses vary in the x, y, z direction and figure shows each quantity due to the dx, dy and dj. So a force is positive if the surface normal points in the positive coordinate direction. Our coordinate system that give the positive, and is negative if normal points in the negative coordinate direction. So the volume forces act on the mass of the volume element. So they include gravity as well as electric, magnetic forces that act on the flow and are denoted by generalized force F, X, Y, Z, that is the component of the T. So see, so here that is the forces, that is the first here shown you the stresses acting on our, that is the fluid element along the x-axis. First that is the showing, it is the, so as I told you, pressure acting along the inwards to the fluid element and stresses always acting outwards of the our given fluid element. So tau, that is the x on the left face acting outward. That's why it is opposite to the coordinate system. Our positive coordinate system is toward right direction along the x-axis, upward along, that is the y or z direction. So here stresses acting on the surface dy dz is towards left side tau x, and due to the fluid element length dx, it changes tau xx plus del y del x of the tau xx into dx. And similarly, the other stresses acting on this fluid element, which is a mark y, that is the double subsuffix tau xy acting along the x-axis and normal, that is the, it is the y direction but changing the length dx. So tau xy plus del y del x, tau xy into dx. Similarly, tau zx, tau zx equal to the tau, that is the del zx or xz divided by del x into dx. Here, that is the stresses, that is the acting along, that is the y direction, and then its effect along the x-axis and y-axis, and due to the length of the fluid element, dx, dy, and dz is shown here. So tau yy, it is acting along y direction, and effect along x-axis is tau yx. Changes its effect due to the length dy is tau yx into divided by del y into dy. All these are the written, the del y del x, del y del y, and del y del z into its components, where that is the from the Taylor series. Third figure written for the z direction. It is written for the z direction. Z direction in these figures is the upward. It is a upward. So this direction. So acting always outward. So that's why tau zz downward, and tau zz plus del y del z into tau zz into dz written upwards, and its effect along the x-axis, y-axis is also given tau zx, tau zy, and due to the fluid element length dz is tau zx plus del y del z into tau zx into dz. So interesting is that when we are considering the stresses along x-axis and the effect along the other axis of the opposite faces, opposite side, you should take the length of the fluid element along that axis. Here we are talking about the z direction, tau zz. So affecting on the other direction due to the fluid element only dz in both y direction and x direction. From the Taylor series you can write. So here change of the momentum rho dx dy is, that is the given del y del t into rho u into dx into dy into dz. This is the our left side. Equal to is nothing, see, rate of change of momentum in a fluid element equal to the momentum influx or entering flux plus leaving flux plus shear stresses plus the weight or mass of the fluid element. All these terms are the right side. So for the right side is the first, that is the flux, that is the influx, that is the here mark rho dot u dot u entering, then leaving, that is the minus rho u dot u. plus del y del x rho dot u into dx through the surface area dy dj. Similarly, for the other side, that is the y and z due to the u. So rho dot v dot u minus rho dot v dot u del y into rho dot v dot u dy into dx dz plus rho dot u dot w minus rho dot u dot w plus del y del z rho dot u dot w dot dz into dx dy. So this is the influx entering and leaving. This is the momentum flux entering minus leaving. So this is the influx momentum. What that is the here it is shown. Then other forces. This is the effects. The forces acting along the x-axis plus stresses. So see again, along x-axis is positive, but here tau x is acting along opposite to the x-axis. That's why it is a minus. And its components or is that is additional due to the dx fluid element is right side. So this is the positive. So minus tau xx plus tau xx plus tau del by del x of the tau x into dx through the area dy dj. Similarly, along the y direction, minus tau yx plus tau yx plus tau yx of the del y into dy through the area dx dz along z direction plus minus tau zx plus tau zx plus del y del z of the tau dz into dz into the dx dy. That you should give you, that is the both side here given and multiply, this yields you del y del t rho dot u plus del y. So see, this will come, that is the minus rho dot u minus rho dot u minus del y del rho dot u dot into dx dy. So this is the written here in the right. So these terms will become, that is the minus written left side, and right side that will become fx, and here minus tau xs plus tau xx that will cancel out, and here it will become del y del x of the tau xx into dx dy dz, and these volume fluid element dx dy dz is cancel out both sides, equal to the here equation number 6. Fx del tau xx del x plus del tau yx into del y plus tau zx into dz. So this is the equation number 7 for the x direction. That's why it is velocity u is written. And similarly, we can write for the y direction. U is replaced by the v. That's all. U is replaced by the v. And here that is the and written equation number 8 along the y direction, z along 9 along the z direction, del y del t rho dot w. So here tau zz divided by del z, that is the z direction. So this is the equations, momentum equations along x-axis, equation number 7, along y-axis, equation number that is the 8, along z-axis, equation number 9. Still, we got the momentum equations in the term of the stresses, and we have to replace these stresses in the term of the velocity. This is not our final aim. This is the mixed type. So let us come on. The pressure can be written from the stress tensor is nothing but the summation of all three normal stresses divided by 3 of the negative. So P equal to the minus tau xx plus tau yy plus tau zz divided by 3 means stresses acting always outwards, whereas pressure always acting inwards. That's why combination of these two equal to 0. So that's why it is written P plus tau xx plus tau yy plus tau zz divided by 3 equal to 0, or minus, it is written in equality. So the minus sign takes into account the pressure and negative now. So the three normal stresses can each be split up into two parts: the pressure and the contribution due to the friction of the fluid. So tau xx is equal to the sigma xx minus p. In the sometimes I told you sigma and tau is doesn't matter normal stress or shear stress. If we should give the double subsuffix, then all are the equal. Means sigma and tau, that is the equal. If you should not give the subsuffix, then sigma is normal stress, tau is the shear stress. Here we have used the double subsuffix, so it is a normal and shear, both are the same, because we are marking the shear. So that's why here mentioning tau is another, that is the replacing by the sigma xx minus p. Tau yy equal to the sigma yy minus p. Tau zz equal to the sigma zz minus p. Then we can replace tau with subsuffix by the sigma and p. Then equations takes the form along x-axis del y del t, that is the rho dot u plus, that is the left side is the remain same, right side that is the changing, and one more term play come in, that is the gradient of the pressure with the negative sign. So fx minus del py del x plus del y del x into sigma xx plus tau y tau del y of the tau y x plus del y del z into tau z. So see, this is the momentum equation along x-axis, which is written for the 7. Here see, simply tau xx, and this is the replace by the sigma with minus del py del a. Similarly, equation number 13 change minus del py del y with sigma yy tau xy, that is the here. So then this is the z axis. Again, we are still we have not got the our required results. Still, we got in the term of the stresses. Then we have to again simplify from some principle of the fluid mechanics, giving the some restrictions. Are you listening or not listening? Or sleeping? Hello.
Listening, sir.
Listening, sir.
Okay, okay, thank you.
Listening, sir.
This that is the very interesting thing. So see. So from the Newtonian here we are restricting, imposing the some, that is the assumptions for Newtonian fluid. Till now we have not used any, that is the restriction. We have written the momentum equations in generalized form without application of the any restriction or any assumptions. Here we are saying Newtonian fluid. And Newtonian fluid, as soon as we are talking, it has some limitations. Means it is also possible in non-Newtonian fluid. So this is the, these relations are only for Newtonian fluid. Sigma xx equal to the 2 dot mu dot del u by del x minus 2 by 3 dot mu dot del u by del x plus del v by del y plus del w by del z. Similarly, we can write sigma yy acting along y-axis normal to, that is the, that equal to the 2 dot mu. So u is replaced by the v and the minus 2 by 3 dot mu remains same. It having the nothing but the continuity term. See the careful. Del dot u by del x plus del v by del y plus del w. So see, these relations are given in the Frank White, Pax MacDonald, and Boundary Layer Theory book by the Celestine, in the rotations of the fluid element, in the torsion, in the translation of the fluid element, they have derived the individually these relations. So these relations you have to not study actually at this level, but still I am giving the Navier-Stokes equations by using these relations. If anybody interesting, then you can go through the boundary layer theory of the first chapter of the Celestine, by the Celestine. All these relations are derived and given. But at this level, you have not asked in the examination such type of the relation, but you must know you should become, that is a citizen of the our Indian culture and go to the for higher relations. So these relations, see, sigma xx, sigma yy, sigma zz. So see, both subsuffix are same, xx, yy, zz. In your term or in the engineering mechanics term, that is the normal stress. Then tau yx means acting on the plane and direction is different than da, and this is the for symmetry condition. Symmetry means tau yx equal to the tau xy, tau zx equal to the tau xz. This is the valid only for symmetry, tau yz equal to the tau zy. So all these are the limitations. Then we can write, we are writing these relations, not arbitrary we are writing. So tau, see, tau xy. See, tau xy, tau yz, tau zx. This is our system. This is our symmetry. That is the in a consequence. So tau xy. So first we have written sub suffix x then y. So first we will derive with respect to the x then y and velocity components opposite to its derivative. So tau xy equal to the mu dot del y del x plus del y del y and velocity components opposite to its derivative. We are writing del x, its opposite velocity component is v. So del vy del x plus del uy the del y. Then xy, then we will come to the yz. So tau yz equal to the mu dot del y plus del y dj del z and velocity components are reverse along of its derivative. So del wy del y plus del vy del. Lastly, we will come on tau zx. Similarly, we can write mu dot del y del z of u plus del y del x of w. And again, I am telling this is valid, that is also for the reverse of the stresses. Tau xy is equal to the tau yx, means symmetry. So these are the our certain assumptions and certain conditions we are imposing to find out the solution of the Navier-Stokes equations. All of you might be aware that the solutions of the generalized Navier equations is very, very difficult. That's why we are imposing so many conditions and we can get the so many solutions of the Navier-Stokes equations. So inserting the normal stresses, shear stresses means sigma xx, sigma xy, according to the Rayleigh equation 16 into the conservation of momentum equations 13, 14, 15, where we have written 13 along x-axis, 14 along y-axis, 15 along the z-axis. We are transforming and inserting all these shear stresses value in the term of the velocity and its derivative. Then these equations will become del. So left side is the same. Again, I am telling. Left side doesn't change because the stresses are available in our equations and relations in the right side. You may see, not that is the, see, this is the for z direction, 14 number, this is the for y direction 13, this is the x-axis for the 12 number. All these are the stresses come into the picture, either normal or shear in the generalized term we are talking. So right side, that is the C, left side remains same, means del y del t equal to int of rho dot u. This is the transient term plus del y del x rho dot u square plus del y of rho dot u dot v plus del y del z of rho dot u dot w. This is the left side remains right side. Fx minus del py del x. Where is change? See 13 number. This is minus, that is the 12 number. Sorry, not 13. 12 number for x axis. Del py del x plus tau y del x of the sigma x plus del y tau yx del y del z of tau z. So del y del x of the sigma x. See, right? So plus del y del x of the sigma xx. What is the sigma xx? See, sigma xx is nothing but the 2 dot mu dot del uy the del x minus 2y3 dot mu dot del u by del x plus del v by del y plus del w by del z. This relation we have to write in place of the sigma x, and this is the sigma x of the del y del x. What it is written in the vector form, this is the del dot v, and del dot v is written all these terms, del uy del x plus del vy del y plus del wy del. This is the written v, del dot v is the velocity vector, not that is. So here reflex direction plus tau, that is the here written. See, plus tau yx y del y, then del y del z tau zx. Their value we have to write. Del y del y and tau, that is the here written, del uy the del y plus del vy the del x tau yx or tau xy plus del y del z of mu dot del wy del x plus del uy the del z tau zx or tau xz. So this is the momentum along the x-axis written from the equation number 12, and these relations of the stresses and velocity gradients, or that is the velocity derived. So here we have written from the x momentum direction. Similarly, we can write for the y momentum x direction. You may see in the left side, product is the v of the square and gradient of the pressure is del y. This is the y direction momentum. Along z direction, product is the z component velocity is in a square in the left side, and gradient of the z of the pressure, that is the momentum equations along z axis. So let us see, all these are the Navier-Stokes equations written here in for the Navier-Stokes equation for three-dimensional unsteady state compressible fluid. Till now we have not taken the fluid flow is incompressible. This is the generalized Navier-Stokes equations. Always remember. Then come on the more modifications. For incompressible flow, we can write for incompressible flow continuity equations del dot v equal to the 0. Then these equations take the form, these term del dot v, that will become 0. Then x momentum, see, x momentum equation, y momentum equations. So see, this is the x momentum equation, this is the y, and this is the y for incompressible. That term will go, that is the eliminated. This minus 2 by 3 del dot v, minus 2 by 3 del dot v. These terms are eliminated due to the incompressibility from the continuity equations. Then it will takes the form in this way: x momentum, y momentum, z momentum. But still it is a unsteady three-dimensional incompressible Navier-Stokes. So here we have written all these equations in the conservative form, means each property of the fluid are written inside the derivative along x-axis, along y-axis, along z-axis. Equation number, all these are written. Up see, that's why mu that is the written here. Left side it is the row is outside, you can write inside also. Let us see if we can expand it, then it will become, see, x-axis del u by the del t plus del y del x u dot u plus del y del v dot u plus del y del z w dot u. How it is written? See, del u by del t plus u dot, one u we have taken outside, del u by del x plus v dot del u by del y plus w del u by the del z, and right side minus del py, minus del py del x. See here, two term, that is the del y del x is equal to 2 dot mu del 2u by the del x square, and these terms will come out two times. See here, you have to make some exercise, then you can make this equation in the generalized form. Here again continuity equation is applied, which is I have not written. Then this equation will become, here continuity equation, see, mu dot del 2u by del x square plus del 2u by del y square plus del 2u by del z square is written from the continuity equation along x-axis. It is not so simple. Again I am telling, it is not. These terms here, minus right side fx minus del p by del x plus del y del x 2 times mu dot del u by del x plus two terms here, del y del y mu dot del u by del y plus del v by del x plus two term del y del z mu dot del 2 plus 2 4 and 2 times here. So there are six terms or five terms, but one term is two times, and ultimately this should become simply del u by del x square plus del u by del y square plus del u by the z square. This is not simply came. Always remember, you have to make some exercise. We have make here also apply the continuity equation. Some term will become zero, del u by del x plus del v by del y plus del u by del z with summed, that is the outside del y del x. You should take common, then it will, you should get it these equations. It is not so simple. Here I have written. So these are the three equations here we got in, that is the Navier-Stokes equations in the form of unknowns are only velocity component and pressure. This is free from the stresses, you can see, and these equations generally used in the our fluid mechanics, heat transfer and anywhere. This is the ultimate equation simply. So this is the velocity. So this is the our given direction. So see, this is the your Navier-Stokes equation I have discussed in detail. In the next class, we should take the some examples. Is it correct? So this is the generalized form of the Navier-Stokes equations. So all of you listen or not listen? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
So see, next class we will take that is the examples. Any query, then ask me. Is it correct? I will send this note. You go through that thoroughly, and you must make that is the how you should got the equations where I told you. That is the, again you have to apply the continuity. Then it will come out this form. These equations are very interesting, and I have given the derivation very illustrate manner. If you have any query, then ask me. Otherwise, today I will not take the attendance. In the next class, I will take the attendance and solve the examples. Okay, thank you.
Thank you,
Thank you,
sir.
sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.